Hello everyone, I'm Zhang Han from Shanghai Jiao Tong University. Here I'll give you a presentation on our work, Dimensionality-Varying diffusion process. First, let's take a quick preview. In this work, we propose DVDP, a novel diffusion process that allows dynamically adjusting the signal dimension. This varying dimensionality enables the reverse process to generate images from much lower dimensional noises. To construct DVDP, we concatenate several diffusion processes with decreasing dimensions by downsampling operations. To ensure the downsampling is approximately reversible, we attenuate the lost data component so that the information loss is small enough. This negligible information loss theoretically guarantees a small difference between the forward and the reverse distribution. Experimental results show the effectiveness of our DVDP and the acceleration on both training and sampling. Now, let's get into more details. It's known that the conventional diffusion model keeps the source signal dimension throughout the entire diffusion process, and this leads to a computationally expensive reverse process. We argue that keeping the dimension is not necessary, and propose our DVDP, which can generate samples from low-dimensional noise. As mentioned before, we construct DVDP by concatenating several diffusion processes with decreasing dimensionality. In the forward process shown by pink arrows, the concatenation is achieved by downsampling operation. And in the reverse process shown by green arrows, it is upsampling operation followed by adding a Gaussian noise. However, downsampling is generally non-reversible, as a high-frequency component will be lost. To ensure a reasonable reverse process, we attenuate this high-frequency component in each diffusion process to limit the information loss. We name such process as attenuated diffusion process, abbreviated as ADP. So, how to construct these ADPs? Take the first two ADPs as an example. The first ADP, denoted as xt0, is decomposed into capital K plus 1 orthogonal components. Each component consists of a data component and a noise component. Lambda bar controls the attenuation of data component. It decreases along time step t, and sigma bar is the standard deviation of added noise. With the definition of xt0, we can define the next ADP, xt1, for each time step t by a downsampling operator, d1. After applying d1, component with subscript 0 will be lost. If we concatenate xt0 and xt1 at time step capital T1, the information loss will be this term. To limit the information loss, we can design lambda bar so that it is small enough at capital T1. Thus, we can approximately recover xt10 in the reverse process by first upsampling xt11 and then adding a noise term. Theorem 1 further guarantees that the approximation error can be small enough. Specifically, it says that the Jensen-Shannon divergence between the forward distribution Q and the reverse distribution P at dimensionality turning point capital Tk is upper bounded by a big O term of lambda bar. Now, let's look at the actual performance of DVDP. Here are some samples on various datasets, including FFHQ with resolution 1024 and 256. Elson Church bedroom cat with resolution 256 and cipher 10. On each dataset, we only use a single unit to model the reverse process. Here are quantitative results on cipher 10 and other 256 resolution datasets. The results show that our proposed DVDP achieves better FID scores on all of the 256 datasets. demonstrating an improved sample quality. Meanwhile, DVDP enjoys improved training and sampling speed. However, FID on Cipher 10 is slightly worse than the baseline DDPM. This is reasonable considering the low resolution of Cipher 10. Here are results on FFHQ 1024. It is hard for diffusion models to generate high-resolution images directly with a single model. Score SDE tries this task, but sample quality is far from reasonable. Cascaded diffusion models perform better in high-resolution image synthesis. It first generates low-resolution images, followed by several conditional diffusion models as super-resolution modules. Compared with these two methods, our DVDP performs better with even smaller number of function evaluations. To show that it's necessary to attenuate the data component, we compare our DVDP with subspace diffusion, which can be seen as a special case of our DVDP without signal attenuation. Here, we change turning point capital T1 and compare their performance. The left figure illustrates that DVDP is consistently better with regard to sample quality. Some samples shown on the right, where the sample quality of subspace diffusion is apparently worse than that of DVDP. Finally, we show that DVDP is effective when the number of downsampling operations varies. We use the same noise schedule for these four different settings. The results indicate that DVDP can vary dimensionality for multiple times. Now let's give a brief summary. In this work, we propose DVDP, a novel diffusion process that allows dynamically adjusting the signal dimension by orthogonal component attenuation and up-down sampling. Theoretically, we prove that the reverse distribution can well approximate the forward distribution. Experiments show that our DVDP can achieve on par or even better synthesis performance than conventional diffusion models with faster training and sampling. We believe that this work can promote the understanding and applications of diffusion models in broader scenarios. Thank you for listening.